Sing by Andrew Drucker.
Thank you, Venkat. And thank you for coming. Let's see. Okay, great. So this talk is about the search for improved algorithms for NP-complete problems like SAT, a set of satisfiable Boolean formulas. So you can keep that as a sort of big picture goal in mind. We believe perhaps P is different from NP, but we can still hope to look for improved algorithms. All right, there's no reason why complete brute force has to be the truth. Indeed, when you look at the literature, the true time complexity, as far as we know, of NP-complete problems seems to have fairly diverse behavior. So for some, like circuit satisfiability, we're stuck. We can't even beat brute force by any superpolynomial factor. For others, we have some kind of exponential speedup. And it also seems that different algorithmic techniques work well for different problems. So what can we say about this situation? What can complexity theory contribute? Well, a basic observation, not new, is that most of the algorithms we have for important problems fit into a reasonably small number of basic frameworks or paradigms, such as dynamic programming algorithms, branching, linear programming, STP-based algorithms, and so on. So an ongoing project of myself and other researchers is to try to identify and formally model some reasonably broad and powerful paradigms for solving NP-complete problems, and try to prove limits on these paradigms for at least some NP-complete problems that help in a way that helps us explain why some problems seem easier than others and why some techniques are amenable in certain cases. And in particular, if you're familiar with things like the exponential time hypothesis, we'd like to, for particular paradigms like these, we'd like to give evidence that exponential time, say, is required for some problems based on evidence or based on assumptions that are weaker or more modest than the ETH. Okay. And we know that there have been powerful results on limits of some of these already. So today's paradigm that I'm going to be talking about is one known as kernelization, but is also can be thought of or is referred to as preprocessing. Okay, so a formal model of this is due to Downey and Fellows and their work on fixed parameter complexity. And the motto of this approach is to, given an input to a hard problem, first try to efficiently shrink that instance. Okay, try to shrink it as much as we can, and then solve the shrunken instance. Okay. So here's the framework. We have some decision problem, L. Think of it as SAT or some other NP-complete problem. And we want to know whether some instance is in L. So a kernelization reduction is a polynomial time reduction, which takes x and maps it to some hopefully smaller x prime. And we require that these two are equivalent as far as membership in L is concerned. The next step in this paradigm is to just solve this reduced instance by some solver, which we can think of as just an exponential time or brute force solver. We're not as concerned with this part here. But once we solve x prime, we know the answer to x. So our focus is going to be squarely on the first part of this picture and in trying to understand what kind of achievable compression amount there is for various problems. Okay. So I guess the high-level motivation for this theory is that preprocessing and this kind of pruning or simplifying of hard instances before applying brute force is a common and useful thing to do. We'd like to give a theoretical account of how much we can achieve just by this first step of efficiently preprocessing. But a cautionary note, if L is NP-complete, then in the worst case, we can't even expect to reliably shrink our instance even by a single bit. And the reason is, if we could do that, we could do it again and again and again, and in polynomial time solve a baby-sized instance, okay? Which gives us the answer for the original. So we have to lower our sights. And what Downey and Fellows suggest is to focus on instances where some input parameter, some measure of the complexity or difficulty of the instance is assumed small. So this leads to this formal model of parameterized problems where each instance comes with a parameter k, a number, giving some notion of its difficulty. And And now we can hope for compression guarantees which take into account not just the input size, but also the input parameter. In particular, one ambitious guarantee is to hope that the output size, the size of x prime, be bounded by some polynomial in k, the parameter, independent of the input size. So k could be much smaller than x itself. This might seem abstract, but we'll get to a concrete example soon. And such a reduction, such a kernelization, is referred to as a polynomial kernel for the input parameter k. All right, so with respect to this measure of complexity of the problem. So it's polynomial in two senses. One, this reduction r is polynomial time, but this polynomial means that the output size has this polynomial guarantee. So this, again, seems ambitious, but actually there are many success stories to this approach to algorithm design. A polynomial kernel is useful for outright solving the problem because a polynomial kernel for an NP problem automatically yields an algorithm with the following runtime. Okay, we have a polynomial factor independent of k for the preprocessing step, and then we have some exponential in k term here for the second solving step. All right, and this runtime is what is known as FPT, or fixed parameter tractable. It's favorable for small values of k. And
Polynomial independent of k. Our reduction should mean
the reduction should run in time polynomial in n, the input length. Yeah. And this gives either the best known or at least competitive FPT algorithms for many NP-complete problems. So let me show you the...
So the reduction cannot depend arbitrarily on k. I'm just wondering why it's not times and it's a plus.
It can be a poly n times f of k, but it's more or less equivalent, yeah. So vertex cover is the classical example. Sam Buss in the 80s gave a polynomial kernel for this problem. Recall that in the vertex cover problem, we have a graph, and we're given a budget k, and we want to know whether G has a vertex cover of size k. That is a set of, at most, k vertices that collectively are adjacent to every one of the edges in this graph. So is this a vertex cover? Not quite. We missed this edge. But if we throw in this green edge, this green vertex, we have a vertex cover. OK, this is an NP-complete problem. So we can't hope to solve it outright. But let's just think about the case where we have a reasonably small budget, where k is small, and we're hoping to simplify our instance on that basis. OK? So suppose k is 3 for this example. And let me highlight this node here, which has high degree. Can we afford to not include this vertex in our cover? No, we can't, because there are too many edges outgoing to it. If we didn't include this vertex, we'd have to include all of its neighbors, and that's too many. So we can simplify this instance. We know that this has to be included. Let's just include it, sort of pluck it out of the graph, simplify, and we reduce our budget by 1. OK? So generally, any vertex of degree more than k must lie in our cover. So we can repeatedly add all of these vertices to our cover until there are no more of them. Or we might run out of budget, okay? In which case we know there's no solution. So
how do you break ties?
there's no tie here. You can just pluck any vertex of degree more than k. So suppose we survive this process. We pluck away all the high degree vertices. The resulting graph, G prime, is of degree at most k. Now, how many edges are left in this graph? There could still be a lot of edges, but if there's too many, I claim that we can't possibly cover them all, because each remaining vertex only covers so many. All right? If they're more than k squared, we're stuck. Otherwise, we've reduced our original graph to an equivalent vertex cover instance where the number of edges is on the order of k squared. And so the number of vertices is also on the order of k squared when you pluck out the irrelevant ones. Okay, so this is a polynomial kernel for this problem. The order of k squared can be reduced to order of k. And yeah, there are many more nice algorithms like this. Okay, so here again is the formal setup for these polynomial kernels. And now I want to start talking about the theory of limits to polynomial kernelization. Okay? That's the focus of my work. So For a long time, there's been some evidence that many NP-complete problems don't have polynomial kernels. For example, the k-clique problem, where I want to find a clique of size k. This is believed not to even have an FPT runtime algorithm. Okay? We would believe that you require something like n to the k, or n to the omega k, time to solve it. So we believe there's no FPT algorithm, and in particular, no polynomial kernelization. But there's been a number of algorithms, or a number of problems, which do have FPT algorithms, but which seem strongly resistant to this polynomial kernelization approach to solving them. And we want to try to understand that phenomenon. So it turns out that by some work beginning in the mid-2000s, that you can rule out polynomial kernels for many more problems under standard assumptions from complexity theory. So the starting point for this theory is two special, what you could call toy problems. Okay, they're parameterized problems which you wouldn't really consider for their own sake, but they turn out to be useful for this theory. Okay, introduced by Bodlander, Downey, Fellows, and Hermelin, and one of them was studied with cryptographic motivations by Harnack and Nauer earlier. So the first is the so-called OR-SAT problem. You're given a collection F1 through Ft of Boolean formulas, each of this particular length k, which you can think of as reasonably small compared to t. And our goal is to decide whether at least one of these FIs is satisfiable. Okay? It's asking about the OR of their satisfiability. There's also the AND-SAT problem, which is the same, but now we want to know whether each one of them is satisfiable individually. So the kernelization task for this AND-SAT problem would be to do the following: to produce a formula phi which is satisfiable if and only if each one of the input formulas is satisfiable. Now, in general, in kernelization, you're allowed to output, an instance of the starting problem. So I could output a list here, but any list can sort of be reduced to a single formula by self-reducibility of SAT. So just think of the output of our reduction as being a single formula. Okay. So we want a reduction like this in the kernelization problem. And to ask for a polynomial kernel would be to demand that phi be of size at most polynomial in k, irrespective of t, the number of instances. Okay? Which would be a powerful thing to do. So for example, one thing that you could try to do is sort of select out of a long list of formulas, the ones that you think are the least likely to be satisfiable, okay? And then sort of compile them into a formula. But we don't know of any way to solve this problem, to produce such a phi. So Bodlander et al. Conjectured that no polynomial kernels exist for these two problems, that you can't hope to do this. Okay. Now, why would they make this conjecture? Well, first, what's the significance of OR-SAT? Well, via a collection of reductions, which can be seen to begin in Harnack and Nauer, and also in Bodlander et al., and with many, many later contributions, we've seen that if this OR-SAT problem doesn't have polynomial kernels, then many other problems don't either. And this is by often straightforward reductions, although some are complex. And one notable example, just to give you one, is the k-path problem. I give you a graph and a number k, and I want a simple non-self-intersecting path of length k. Okay? You'd like to somehow condense this problem to one on a small graph with something on the order of poly k vertices. We don't know how to do this, and in view of this conjecture, maybe it's not possible.
So just to get the parameters clear, so you said each, in the OR-SAT problem, each SAT instance is size
at k. Yeah.
And the number is t, and that's an independent parameter from
t can be arbitrarily large compared to k, although you can you can think of it as something growing slightly super polynomially with k, for example. But the reduction should be polynomial time in the size of the input list.
And then you want to shrink it to a single SAT problem whose size is poly k, independent of t. 'Cause, 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 'cause,
Although we would be happy for even more modest compression amounts, and I'll talk about that a little too. For the ANSAT problem, these authors showed that if ANSAT doesn't have polynomial kernels, then a different list of problems doesn't have polynomial kernels as a result. So it has a different kind of explanatory power. And it doesn't seem to be as wide in its explanatory power as the ORSAT problem, but still some nice problems. And maybe the most notable example is the tree width problem of determining the tree width of a graph, which is a very important quantity for dynamic programming-based algorithms to solve graph problems. Okay. So these problems all have FPT algorithms, as I mentioned. And so what the OR and AND conjectures would imply is that kernelization can't even match the best known runtimes for these problems, let alone beat them. So this points to an inherent weakness on this paradigm for specific classes of NP-complete problems. It helps us understand the diversity of NP-complete problems themselves with respect to their solvability by various paradigms. Okay, so why should we believe these OR and AND conjectures? Do we just need to accept them as new conjectures? Well, actually we have some evidence based on a standard complexity theoretic assumption that NP is not contained in co-NP poly. If you believe that the polynomial hierarchy is infinite, for example, you've got to believe this as well. And this, informally speaking, this assumption can be glossed over as saying that there are no short proofs of unsatisfiability of Boolean formulas, even if you allow some non-uniform advice or non-uniform information in defining your proof systems. Okay. So under this assumption, shortly after Bolender et al.'s work, Fortnow and Santanum showed that indeed there are no polynomial kernels for the ORSAT problem. And the ANSAT problem was a bit trickier, but in 2012, I showed that under the same assumption, no polynomial kernels for this problem either. And indeed, I'm able to extend both of these results to randomized kernelization, where there's some small probability of error in the reduction. Both results are somewhat stronger quantitatively than what's stated here, but these are just succinct statements. And let me also just mention that I prove a similar negative result for a notion of quantum compression. It's sort of some kind of a quantum analog of kernelization that I defined in the paper, but I'm not going to discuss that any further. Okay, so let's talk about the proofs ideas for my work. How much time do I have? So what we do is yes.
Why do you talk about ANSAT instead of like KCSP?
Good. So the ANSAT is a collection of distinct SAT instances, which you can think of as being on distinct or disjoint variable sets. So it's not.
You might have like a KCSP, you would have like constraints on K variables and of those together. So it matters to you that you have.
Well, KCSP is like a bunch of constraints on a common set of variables.
Right, but each constraint, if I made K be the number of variables.
But think of a KCNF. Each one of these CNFs, or each one of these clauses, is individually satisfiable. And so if you look at the AND of individual clauses, each one is satisfiable, and so it's easy to solve such a thing in our notion.
Sorry.
It's okay.
I didn't understand. Thanks.
Okay. So our approach is to assume that we have a polynomial kernel for ANSAT by contrapositive, and then use it to show that NP is in co-NP poly. And by work of Babai, Moran, Goldwasser, and Sipser on interactive proof systems, it's enough to give so-called Arthur-Merlin proofs for the unsatisfiability of Boolean formulas. So it's enough to show how a computationally powerful Merlin can convince a computationally bounded and skeptical Arthur that a given formula is unsatisfiable. Okay, so we have a polynomial kernel for the ANSAT problem. It looks like this. Take some number of formulas, outputs a formula. What are its properties? First of all, we're going to restrict attention to the case where all of these FIs are of some length k, and let's assume that T is a large polynomial in K. The number that we're going to feed to this reduction is a large polynomial in K. And remember that we have a compression bound. We have an output size bound on this formula phi. And we choose this t large enough so that this output size bound is on the order of t log t. Okay? When you have this kind of bound, that will be the regime in which we can apply the techniques and use this artifact to prove unsatisfiability of Boolean formulas. Okay? If you have a polynomial kernel for ansat, you can always choose t large enough such that this holds. Indeed, you can even get t large enough so that phi is of size much less than t. But we can get quantitatively stronger results in this range. Okay, now the correctness properties. Firstly, if all of these formulas are satisfiable, I'm going to use green to denote satisfiable formulas, then the output is satisfiable as well. But if even one of them is unsatisfiable, or red, then the output is unsat. Okay, so those are the two properties that we have. And now we want to use this thing. So,
what are we assuming about the variable sets?
The variable sets? So again, think of these as individual sat instances. They can each be on their own variable set.
They will or they can?
Either way, the way we define it is just that we just want to know whether they're all individually satisfiable. So it doesn't matter really, but yeah. Okay. So we have a Boolean formula G of length k, a single formula. And Merlin claims that G is unsat. So what does Arthur do to check this possibly bogus claim? Okay. So the first thing that Arthur is going to do is ask for some privacy. This will be a private coin protocol. So he retreats to his king's quarters. Now, we're going to use this reduction, this polynomial kernel, for the ansat problem. So we need to generate some inputs to this thing. So the first thing that Arthur is going to do is generate some potential inputs to our compression reduction. Okay? He's going to generate f1 through ft according to some probability distribution. Now, which probability distribution? That's really the heart of the matter. But for now, just think of it as some distribution. Next, Arthur's going to flip a coin. If the coin is heads, he's going to directly stick these formulas into our reduction, outputting a formula phi. And note that in this case, these formulas that we generate are always going to be satisfiable. So in this case, the output formula will be satisfiable. If the coin lands tails, however, then Arthur's going to use this formula G that Merlin claims is unsatisfiable. And he's going to stick G into one of the positions to the inputs to our reduction. Namely, he's going to choose a random position between 1 and t and insert G there. Okay? And again, he'll plug these in, and he'll get a formula, which, if Merlin was telling the truth, this would be an unsatisfiable formula. Finally, in either case, he sends the formula to Merlin. Okay? And Merlin's job is to guess which way the coin landed. Okay? We're going to accept Merlin's claim about G if and only if Merlin can correctly guess the coin value. Okay, so in this case, where G is truly unsatisfiable, as claimed, then indeed Merlin learns the coin flip value just by looking at the sat status of what he gets. So he can confidently answer. However, suppose that Merlin was lying and G is satisfiable. Then, in this case, what Merlin gets is always satisfiable. So he can't use that decision rule to answer this quiz. Okay? So we at least have the potential to confuse Merlin. Okay? But Merlin's, a very clever guy, so he could use other criteria to try to see which case we're in. So we really have to work somehow to choose these f1 through ft's in the right way that will cause Merlin to be confused. Okay, so the main technical lemma then is that we can do this. There exists an efficiently samplable distribution over these formulas. It's not a product distribution. That has the following property. For any satisfiable G that Merlin might try to lie about, the output distribution of this reduction is not too strongly affected by the insertion of G at a random coordinate. Okay?
It's not too strong.
One negation to...
Oops, not too strongly affected. Sorry about that. More precisely, the two cases that Arthur could use where G is or is not inserted into the reduction, the outputs are at statistical distance noticeably less than 1 between those two cases. Okay? And this confuses Merlin, because no matter how smart he is, if these two distributions, they might be being sent, are somewhat overlap, then there's no way he can reliably distinguish the two. Questions about this? I should say efficiently sampleable with non-uniform information. Okay. That's the asterisk. And the proof starts to involve some information theory, which is why I volunteered this talk, and exploits the fact that the output size is not too large. Okay? So, the first step is to simplify our lives a little bit. Remember, we want this distribution which disguises the insertion of an arbitrary G, an arbitrary satisfiable G. But let's just simplify our lives and imagine that G is drawn from some fixed known distribution D. Okay? So in this case, how should we respond? What kind of inputs should we choose in this case? Well, I think it's natural to guess that they should look as much like G as possible. So let's just sample these things independently from D itself. Okay? So that's our response in this special case. Okay? And indeed, this works. For most positions I, fixing the input as G doesn't affect the output distribution by too much. Okay? Namely, the pre- and post-output distributions have noticeably close statistical distance. And the proof really follows from some closely similar facts in the literature, as far back as Raz's work on the PRT, but also Klauck, Nyack, Tashma, and Zuckerman prove much the same kind of result in a more powerful quantum communication setting. And I just want to mention a couple things that are slightly different, although they don't really involve any technical work or more technical work. The first is that we really need to, in our argument, want to handle an arbitrary distribution here and assert this for an arbitrary distribution and combine this fact. Okay, so it's not enough to just look at, say, the uniform distribution. And the second is that for quantitatively strong results, to handle the case where the output size is as large as t log t, it helps us to use not only the Pinsker inequality, which is a classic information theoretic tool used in those earlier works I mentioned, but also a somewhat lesser known result of Vajda, which says that two distributions are noticeably far apart as long as their divergence or relative entropy is logarithmically bounded. Okay, so there are these two nice things which can be used to handle two different ranges of the output size bound. Okay. So based on this fact, we succeed in our task of disguising the insertion of G, assuming G is drawn from some known distribution D, but it can be an arbitrary distribution.
But also, didn't we want F1 through Ft to be satisfied?
Yes, but we're assuming that G is itself is satisfiable. We're just looking at the case where Merlin is lying and his claimed unsat formula is really sat.
It's all the time.
Yeah. So the next step is to view this process as a two-player game. Player 1 is tasked with choosing G, the satisfiable formula. And player 2 is being asked to choose this distribution over F1 through Ft. And player 2's goal is to disguise the insertion of G, okay, so that the output of R is not affected too much in statistical distance. So informally, let me say that player 2 wins if the distribution, the output distribution of R disguises the insertion of G. And so that the output distribution of R is not too much different according to whether or not G was inserted. So the previous claim that I made can be rephrased as saying that for every mixed strategy of player 1, for every distribution of possible choices of player 1 of this formula G, there is an appropriate response for player 2, namely T independent copies drawn from D. Okay. And so this recalls a powerful result of game theory, the minimax theorem, which says that because we can beat any mixed strategy of the first players over choosing G, there actually exists a single mixed strategy for the second player that wins against any G. So we're powerfully boosting our result here. So there's a single distribution over these things that wins against all G, which is what we wanted in the first place. The only hitch is that this magic distribution that we got in this way won't be efficiently samplable because the minimax theorem is not really fully constructive. So we need further work to achieve that, and several steps involving sort of modifying the strategies that player 2 was using some approximate minimax theorems, and so on. But this is the basic idea. So I'll stop there. In conclusion, kernelization is a paradigm that's powerful enough to have many success stories, many nice algorithms to its name, yet also meaningfully restrictive enough that we can prove stronger limits for this class of algorithms. And I think it's interesting to continue to try to prove strong limits on more paradigms of NP problems, and perhaps using information theoretic ideas along the way. So, thank you.